In this next video, we're going to keep using the chain rule, but we're going to do it for functions that are given to us in different ways, because not every function has to be an equation, a quadratic or sine or cosine. Sometimes functions are given to us as graphs that don't necessarily have an equation that goes with it. I know that these do, but that's besides the point. And sometimes functions are given to us as tables, and we don't really have any connecting values. We don't know if there's a pattern or a rule or anything like that. But we can still find the derivatives based on what's given to us. So, we are being asked to find h prime of 7.5. But one thing that's really important to note is that if you're going to be asked to find h prime of 7.5, I'm not going to do this using the f prime of c definition we learned a couple of weeks ago. I'm not going to do that anymore. What I'm going to do is find h prime of x and then plug in 7.5. That is really important. We're going to see this a lot in a bunch of different ways throughout the year. We find h prime of x first without plugging in any numbers. And since h of x is simply a composition of f of g of x, its derivative is the derivative of the outside, evaluated at the inside, times the derivative of the inside. So write that out first. Then we can plug in the 7.5. Notice how my labels are very important here. You absolutely cannot call this h prime of 7.5. Absolutely not. Because it's h prime of x. And you definitely can't say h prime of x equals something with 7.5 in here. Definitely can't do that. Make sure you're very careful with the names you give everything. But we can plug in the 7.5, f prime of g of 7.5. Notice how it's not f prime of 7.5. It's f prime of g of 7.5. So I am going to have to find that first, times g prime of 7.5. So order of operations tells me to do what's on the inside first. So f prime g of 7.5, that's up here. Well, that equals 3. G prime of 7.5, this is where it's helpful to notice that g itself is linear. So the slope of g is going to be the derivative at all points. So if I do a quick measure up to 2 over 3, the slope of this guy is 2/3. So h prime of 7.5 is f prime of 3 times 2/3. Well, I need to keep going because I need to find out what f prime of 3 is. Notice how when I actually do the plugging into f prime to find the derivative, it has nothing to do with the 7.5 anymore. I'm looking for f prime of 3, which would be the instantaneous rate of change on my blue f function when x is 3, and you can see that in this quadratic, the maximum value, the vertex, is when x is 3, which means the derivative at that point, where there's a horizontal tangent, is 0, which means that h prime of 7.5 itself is also 0. We're going to do the almost exact same thing with a table of values. Notice how this time the h of x is flipped around. This time my h of x is g of f of x. It's a different function, different order. So if they ask me to find d dx of h of x evaluated at x equals 3, which is a big fancy way of saying h prime of 3. I certainly expect you to use this notation more, but I just want to make sure you're not scared off when you see something like this. Just decode it, translate it, figure out what it means, and work with it. So again, we need to find h prime of x first. Be real careful about the order. This time g is the outside function, evaluated f of x, times the derivative of that inside function. So now I can find h prime of 3, g prime of f of 3 times f prime of 3, and we can just use the table to fill in whatever values we need. I can't look at the g prime column yet. I can't look at that yet because I don't know what to evaluate it at yet. First, I need to figure out what f of 3 is. So I'm going to use that too. Then f prime of 3 is negative 5. Now I can look at my g prime column and say g prime of 2 is 15. And so the whole thing, h prime of 3, is equal to 15 times negative 5, which is negative 75. And one last quick thing to show you, although it's actually not that quick, is sometimes the chain rule goes multiple levels, more than one step. Because if you look at this function, there's actually 3 steps here. There is, the outside function is sine of x. But then inside of that sine is a square root. It's the sine of a square root. And then inside that square root is a polynomial. So my derivative has 3 steps. It's very important to know which ones come first. So I'm going to take the derivative of the most outside one as cosine of whatever's inside of it. Right? The outer function was sine, its derivative is cosine. But keep in mind what I keep saying, that the inner part, the inside of that derivative has to be exactly the same as what we saw already. Can't take the derivative of that yet. Now I can take the derivative of the square root, multiply by the derivative of that square root, but keep in mind that inside of that square root was the polynomial still. So yes, I can take the derivative of the square root, which is 1 over 2 times the square root. But just keep in mind that whatever was inside the square root is still there. I haven't addressed the 2x cubed minus 5x yet. Still there. And now I can multiply by the derivative of the innermost inside. Derivative of 2x cubed minus 5x is 6x squared minus 5. I can put all of this together. The cosine, well actually I'm going to put the 6x squared minus 5 first, times the cosine of the square root of 2x cubed minus 5x, all over 2 times the square root of 2x cubed minus 5x.